Hi, my name is Knoll from Intel Corporation, and I'm here today to talk about the oneAPI Rendering Toolkit and how we've used it in Cosmology visualization as part of this application Spotlight in Cosmology for IEEE Visweek 2020. I'll briefly introduce the Intel oneAPI Rendering Toolkit, or as we call it, the Render Kit, which is Intel's open source software suite for advanced rendering and visualization, especially helping with high-performance computing visualization and professional viz needs. It consists of Intel Embry, which is a low-level kernel library for efficient BVH building, traversal, and primitive intersection. The Open Volume Kernel Library, which is designed for volume structure abstraction and effective sampling and filtering of volumes and traversal as well. Osprey, which is the high-level render graph API, which ties the lower-level pieces of the render kit together and exposes them to software such as ParaView and Visit through this API. And then we have software, for example, Open Image Denoise, which is a denoiser for path-traced images, Open Swir, which is a fast software rasterizer, and Osprey Studio, which is a highest level front end that we use for professional visualization and quick demos and proofs of concept. Together, these are the render kit. The Render Kit software stack looks more or less like this. At the very top of the stack, you'd have an end-user application, for example, ParaView or Visit, or possibly Osprey Studio. At the middle level of the stack, you have Osprey and family products, for example, Osprey MPI, that expose the interface. And then at the low level of the stack, you'd have the component libraries, for example, Embry, OpenVKL, Open Image Denoise. And at the bottom, you have the hardware, for example, Intel Xeon or Core CPU architectures or the upcoming Intel Xe GPU architectures. Now to discuss Cosmology Viz. When we've seen Cosmology visualization problems in the past, we've noticed that they tend to be different from a lot of other viz in some ways. First of all, they tend to have a lot of multi-physics and multi-structure data. So for example, in one cosmology simulation, you can have structure data alongside particle data. You can have adaptive mesh refinement data alongside both of them. So there's not really a one-size-fits-all type of data that you want to render. Simulations can be very large. They can be in the order of trillions of particles for some of the hack capability runs that we're currently looking at. And you can have 10K cubed to 16K cubed structured volumes in the case of the flash data that we visualize later on. And right there you get into terabytes per time step and potentially petabytes or exabytes across an entire simulation run. Very rarely are these data saved out to disk in their entirety, so you really are working with in situ methods and better batch techniques. Partly because of this, there's a lot of emphasis on data triage and reduction techniques and really trying to focus in on what you're looking at inside the simulation. So there are techniques, for example, halo finding in large-scale cosmology visualization. And there are also other conversion techniques, data reduction techniques like converting to structured data via an SPH filter. And as a result of that, there's not really always a right visualization modality or a single right visualization modality that you want to use for Cosmology Viz. And in this talk, I'm focusing more on the general rendering problems as opposed to the more tricky question of how do you correctly visualize large-scale cosmology data. But there isn't really a one-size-fits-all solution for this. In general, in this talk, we'll mostly cover volume rendering. And for this, I'll briefly talk about the Intel Open Volume Kernel Library, or OpenVKL. OpenVKL is a set of scalar and vector kernels for sampling and traversing volume data. And really what it does most is abstract volume structure. So we can have one API that covers structured, unstructured, AMR, or particle data, or other types of volume data. And then you have a set of interfaces, sampler, iterator, observer, and filter interfaces that let you operate on these volume data sets regardless of their underlying structure. Recently, we added particle volumes as a capability. I'll talk about that very briefly. And there's ongoing ISBC on XPU development in OpenVKL. The other piece of software that is most relevant to cosmology visualization is Osprey, which is the high-level render graph API for scientific and professional visualization. I won't talk too much about Osprey itself and the Osprey API, but I will mention the family products, Osprey MPI and VTK Osprey. Osprey MPI allows Osprey objects to be specified in an MPI cluster environment, and then you can render either in replicated mode with replicated data, and there you can use full path tracing techniques, or you can use raycasting or partial ambient occlusion techniques to render distributed data. And that second one is what we're especially interested in when you're talking about terascale per time step volume data coming out of cosmology simulation, for example, what we've done with Flash. I'll also mention VTK Osprey, which exposes Osprey into VTK and is used in the Osprey integrations in both ParaView and Visit. This is open source, developed in partnership with Kitware, and it's upstreamed into VTK directly. We're also using this as the basis for the Kronos-Inari specification, which would be a cross-vendor way of tying lower-level ray tracers into ParaView and Visit. And there's more information on that on the Kronos-Inari website. The most recent piece of work that we've done directly for cosmology is particle volumes in OpenVKL 0.10. And this is an ongoing collaboration with folks at Argonne National Laboratory and Los Alamos National Laboratory. Particle volumes are a three-dimensional RBF, radial basis function, or also known as a smooth particle hydrodynamics, or SPH model. And they're really a scalar field that's defined as the sum of Gaussians, as you can see. This is implemented in OpenVKL using Embry BVH builders and then traversed in a custom traversal inside OpenVKL. And what's great about this is that it supports volume path tracing using the full OpenVKL API. So it's like any other volume that you'd have in OpenVKL. And here we have an image of relatively small, roughly 6 million particle dark sky hack data. That's volume path traced in OpenVKL. Work that we've done several years ago and we've continued to maintain and improve in OpenVKL is, and Osprey, is AMR rendering, adaptive mesh refinement rendering. In particular, block-structured AMR, namely GR Chombo. This is a collaboration we've had with Paul Shellard at the Stephen Hawking Center for Theoretical Cosmology at Cambridge, and Carson Brownlee at Intel, in particular, has done a lot of work both on the implementation and the production side to really see it come to light. It's based on a paper that we had at SIGGRAPH Asia in 2017. The SIGGRAPH Asia Symposium on Visualization. It was originally implemented in Osprey 1, and now it's fully exposed in OpenVKL and Osprey 2. So the video on the right, the boson star formation, actually leverages path tracing in OpenVKL. And the last application I'll focus on is distributed volume rendering with Osprey MPI. Osprey MPI, as you remember, is a full Osprey device implementation for MPI in a cluster. And when you use Osprey MPI, you can either have data that are distributed, so you have different data on each node, or replicated. And when we're looking at terascale cosmology data, for example, this 4 terabyte flash data set, you definitely want to use distributed data rendering. And this is based on two recent papers in Eurovis 2019 and a recent book chapter in the In Situ Visualization for Computational Science series that describes the algorithms that implement this. The demo you see on the right is a 4 terabyte 10K cube flash data set, which was rendering interactively on 27 nodes of Rentera at TAC. Interestingly, this rendered roughly 140 times faster than an equivalent in Visit, and that's just purely because of the fewer nodes we're using, the larger memory per node footprint that we're able to take advantage of, and the efficiency of oneAPI. And that concludes my talk. Thank you very much for your attention.